fairly impassioned. Whatever. Okay. Don't click that. Just go. Okay. Any questions on the lab? Yes.
Number 3, please.
On which page?
Page 3, number 3.
What's the question?
What has to occur to change the slope of the
Oh,
velocity?
both God. Okay. There's your velocity time graph, right? Whatever it is. Okay? This is a logic problem. Okay? What does the slope of a velocity time graph represent? Acceleration, right? So at this point, does the acceleration change? Yes. How do you know the acceleration changes? Oh, no. This is the velocity time graph. You're not changing direction here. The slope changes, right? Now, even if the slope is going like this, okay? Going like this, and then, you get some action like that, okay? So, this is, the slope doesn't even have to change sign. All I'm asking you is, well, what do you have to do to change the slope, right? So if the slope represents acceleration, what are you going to have to change? The acceleration. What is acceleration? So how does acceleration fit into into Newton's second law? F equals ma.
So you have to change the equal.
Yeah. Then what do you do to change the force? That you're on your own.
Oh, can you give me a rough estimate?
It's not a number. That's a number.
No. Okay, now let's talk prelims. On the back side, on questions 5 and 6. Okay? On questions 5 and 6, like for example, on number 5, you wanted acceleration to be negative 1.10 meters per second squared. And on number 6, you want an acceleration of 0.20 meters per second squared. Okay? Now, if you took 5,000 kilograms and multiplied that by the mass, okay, and in this case you'd get 1,000 newtons, okay, and if that's all you did, you're wrong,
Why?
okay?
The gravity mafia.
Yeah, because here's the deal. When you look at all the forces, force applied, force opposing, net force, whatever, when you multiply mass by acceleration, what is the only force that equals mass times acceleration?
Net force.
Net force. Not FAP, not FOP, not force, nothing. Only and only net force equals mass times acceleration. Now, let's just think this through. Okay? Let's just think this through. You're talking, and this is why I emphasize this thing is going vertical. Okay? Vertically, if you're talking about any vertical motion, what force always has to be accounted for?
Gravity.
Gravity. So no matter what, it's like that. Or you got to pay the mafia. Okay? No matter what, this has to be taken into account. What's the only situation? There's two situations where you don't have to worry about that.
DD space.
DD space, or in this lab,
Horizontal.
horizontal motion. Okay, because there's no horizontal gravity. Because when I drop this pin, what direction do I know that pin is going to fall?
Down.
Straight towards the center of the earth, right? I don't have to worry about dropping this pin and all of a sudden it's going to go off in a diagonal, which would be really weird. Okay? I know when I drop that pin, it's going to fall straight down. Why does it fall straight down? That's the only direction that there is an imbalanced force. There's no imbalanced forces horizontally. It isn't like I let go of it and it starts to drift sideways, which would be really weird. Okay? It's like, oh, gravity's sideways now. Whoa, that changes everything. Okay? No, you know it's going to act towards the center of the earth. So, now, just think this through. I beg of you, think this through. Let's actually start with number 6. You want an upward acceleration of 0.2. Now, when you have a positive acceleration, does that also mean that you have to be going up in the air? Like you have to be going away from the surface of the moon? No, your acceleration does not tell you which direction that you're going. Okay? Just like I throw this pin up in the air. Gravity, if gravity is the only force acting on it, I don't know which direction the pin is going. Gravity might be making it slow down. Gravity might be making it speed up. I don't know. All I know is that gravity is the unbalanced force acting on it. So don't confuse a negative acceleration with negative velocity, okay? It might have it, but that doesn't mean it's got to be, right?
I understand all that, but then I also confuse myself because, like, I remember that force net goes in the same direction as acceleration. So
This is true,
how do we not confuse that?
okay? But here's my point, okay? Let's say that you have velocity vectors that are pointing up and they're getting smaller. What's the direction of your acceleration vector? Your velocity vectors are pointing up, but they're getting, so it's slowing down, going up.
Oh, okay, so it's down.
Yeah, so this has negative acceleration, right? That's going to be pointing down. Now, if I have velocity vectors that are pointing down and getting bigger, what's the direction of my acceleration vector?
Oh, sorry.
I've got velocity vectors that are pointing down and getting bigger.
Down, sorry.
So yeah, now I have negative acceleration. So in both situations, I have the exact same acceleration vector. But in that situation, that acceleration is making it go slower. This acceleration is making it go faster. So that's why just because you have negative acceleration, that doesn't mean that you know which direction that you're going. You just know that that's the direction of your acceleration vector. Does that make sense? Okay. Now, I'm going to have a positive acceleration on number 6. Does my answer have to be bigger or smaller than 8,350?
Bigger.
Bigger. Why?
Because remember,
Because you have to overcome that force to go up.
Yeah. What if my applied force was exactly 8,350 newtons? What would happen? Yeah, it either would be moving up at a constant velocity or down at a constant velocity. Okay? You don't know. You just have a constant velocity. So, if you're going to have a positive acceleration, your applied force has to be bigger than gravity. Now, here I want a negative acceleration. Okay? So does my answer to number 5 have to be a bigger number that's bigger or smaller than 8,350? Smaller. Does my answer to number 5 have to be a negative number? No. No, because if your answer to 5 or 6 is negative, that means that you have flipped this ship completely over and you're firing it down. Okay? Probably not a good idea. NASA would probably frown on that. Like, what are you doing? I decided to flip the ship upside down. Really? Good. So, you have to keep in mind the difference between fap, fop, and finette. Okay? It is the most vital thing that you have to keep straight. And remember, it is only the net force that equals mass times acceleration. Nothing else. Okay? Nothing else. Make sure on that velocity time graph that I clearly see what you want to be positive, what you want to be negative, and whether it's speeding up or slowing down. Okay? So if you're going to do like some weird answer key, like, oh, squiggly lines mean it's speeding up, and slash lines, whatever, I don't care. Okay? Or you can just use arrows, which is about as easy. But make sure that I see exactly what you have going on. Okay? Anything else? Going once? Going twice? Mary, did you have a question? Or
No,
just,
I didn't.
okay.
was just picturing-
I saw the little, okay.
Yeah.
So get those handed in. So let's say that we do this. So I've got a 500 gram mass on this Earth, okay? Just, we're not on the moon, we're here. So I got a 500 gram mass. So here's my question. How much upward force do I have to exert to hold up this 500 gram mass?
4.9 newtons.
Why 4.9 newtons, Honest?
Because gravity's 9.8. And
Oh, did you seriously,
Gravitational acceleration.
Did you seriously say gravity is 9.8?
I did.
It's not
Do you see why I'm giving you the evil physics scowl?
Yeah, gravitational acceleration.
Is,
9.8 meters per second squared.
okay? So what?
Okay, so we know force is equal to mass times gravity. So if I,
You said gravity.
Acceleration.
yeah, this is just the way my brain thinks about it.
Hey, this is how my face reacts to your brain thinking.
Okay.
No!
That makes me feel sad. Okay.
So we just take Homer from the
I
This is
feel
why I
like
have gray hair. So, perhaps mass times
acceleration,
due to,
gravity.
there you go. Okay, and the strange rock that we're on has a gravitational acceleration of,
9.8 meters per second squared.
beautiful. Okay, there we go. Physics class, give it up. There we go. I heard that there was some university, I don't remember where it was. I just read this, like, they thought that applauding was like intimidating to people, so now they only do like jazz hands. It's like, seriously.
This is scarier.
I know it's creepy.
Because you have a whole like auditorium of people going
You mean
at you.
Berg and his paws?
That's really scary. He's gonna beat you.
Okay.
Michael
You
Jordan.
could like squeeze someone's head and just look.
Berg, you should have been a wide receiver.
Like the antagonist in every movie, would squeeze the head and crack.
Berg didn't want
Dude,
to
what are you on?
Okay.
Okay,
Think of that.
I don't think.
Think of all the physics you could do. You could be like Odell Beckham right now.
I could be.
He could be varsity
I
in
could be.
baseball.
Berg was too soft for that.
Called you Charmin
You want to talk who's fluffy right now? Come on.
Oh my god, I got personal.
I didn't start it, but I finished it. Okay.
He doesn't think so I can't say anything else.
Huh?
Nothing.
What? McGriddle? Okay. So, here's the deal. So, the strange rock that we're on has a gravitational field, which is a good thing, because if we didn't have one, we wouldn't be here having this discussion. So, Honus says, oh, look, 0.5 kilograms multiplied by the acceleration due to gravity, 9.8 meters per second squared, yields a force of 4.9 newtons. So, all of this material was being pulled down with a force of 4.9 newtons. Therefore, to balance that out, I have to apply an upward force of 4.9 newtons. Cool, right? Now, if I want this thing to accelerate upward, am I going to have to apply more force or less force than 4.9 newtons? Why?
Because you want the net force to be pointing upwards.
Okay, so at a minimum, to make it accelerate upward, how much do I have to apply?
5.
5, okay? Even if I apply 5 newtons of force upward, I got a negative 4.9 going down, that's going to produce a positive net force, right? Now, if I want it to accelerate downward, how much force am I going to apply?
Less than.
Less than, okay, right? Momentarily, I get to apply less than 4.9 newtons. That's what's going to happen. Now, with that in mind, this is going to sound creepy at the beginning, but stay with me. It's a science thing. So, imagine that you're in a hotel. That isn't the creepy part. The creepy part comes from the fact that you walk into the hotel wearing a trench coat, and inside the trench coat you have a bathroom scale. That's the creepy part. So, but it's in the name of science, so it's okay. So you walk into the elevator and you put the bathroom scale down, and you quickly close the doors so that no one sees you, and you look down on the bathroom scale, and let's say that, and you have the nerdy bathroom scale that weighs in newtons, okay? And you look down, and the reading on the scale is 700 newtons, okay? It's not in pounds, it's not in kilograms. You have the nerdy physics scale that measures in newtons. So, you close the door, right? Door's closed, miracle of miracles. Then you're going to go up to the 10th floor, right? When the elevator begins to accelerate upward, what's going to happen to the reading on the scale? Is it going to be more than 700 newtons, like maybe 750? Is it going to just stay at 700 newtons because gravity isn't changing? Or is it going to be less than 700 newtons? Olivia?
It's gonna be more.
You say that with absolutely no confidence.
Yeah, it's in the bus.
Let me give you a hint, be sure.
I'm sure it's more,
Why?
because that bottom of the elevator is pushing up maybe,
To balance out,
to balance out gravity,
okay? Keep going,
and then he's pushing down on the elevator too.
okay? Keep going.
Which means he weighs more.
He weighs
Or
more.
he doesn't weigh more. He's putting more force down on the bottom of the elevator.
Okay? You're 99% right, which is pretty good. Okay? So, here's what you have to understand. What is the scale measuring?
Wait. Oh, I'm sorry. No, we're so sorry. Yep.
Force. Is the scale reading FAP, FOP, or FINET?
No.
How many vote that it's measuring your applied force? How many vote that you're measuring the opposing force? How many vote that it's measuring your net force? The one lone voice.
I wanted to be different.
I said finesse.
You said
Don't be
FINET.
wrong to
I
be
saw
different.
everyone seeing me and I was like,
See, I said with my answer. I'm my own
Welcome
person.
to politics in America.
I was supposed to do it.
Okay.
sad truth.
Now, let's think this through. When you're standing there and the elevator is not moving, what is the net force acting on you?
0.
0. So if this was measuring net force, what would the scale be reading?
0.
It's balanced out.
Because it's balanced out, right? So that leaves either FAP or FOP. Now, in this situation, what's your opposing force? Gravity, right? So gravity is pulling down with a force of, if you want to make that negative 700 newtons, right? Okay? True?
Yes.
Now, here's the deal. If you go back to what Olivia said, when you push the up button, what's going to happen to the reading on the scale?
Go up.
It's going to go up, maybe like 720, 740, something like that, right? So here's my point. If this was reading the gravitational force, it would never change. It would stay at exactly at 700 newtons. Because gravity, your gravitational force is not going to change based upon that elevator going up or down. So that leaves us with the fact that the scale is measuring your applied force. Yes?
But yesterday you said that it's not going to change by that much, so it wouldn't change at all.
No. This isn't going to change at all. You're right.
But you said like when you go up, it wouldn't.
But because you're accelerating upward. But that's what I'm telling you. But the scale itself is measuring your applied force.
Okay, so your
Not your
mass
opposing
doesn't actually
force.
change, but the accelerations would change.
Yes.
I got it now.
Okay.
But would acceleration change only on the way up? Or
Oh, no. Okay, visualize this. Oh. So, let's say that you were to look at a force versus time graph, okay? And imagine this. You're starting at the bottom. You're going to accelerate upward. Then you're going to maintain a constant velocity, and then you're going to slow down a little bit once you get to like the 10th floor, okay? When you press the up button and those doors close, is this elevator going to accelerate?
Yes.
Yes, that requires an imbalanced force, right? So when you're just standing there, that scale is reading, oh, that got weird. 700 newtons, right? Now, the doors close, and you begin to accelerate upward. What's the reading on the scale going to do? It's going to go up a little bit, right? It's going to go up while you're accelerating. But then, what's going to happen to the reading on the scale? Once you reach a constant velocity, it's going to go back to
700.
700.
Got it.
Because once you move at a constant velocity, everything's balanced out again. So then it's going to drop back down to 700. So this is while you're accelerating. So this is when your applied force is bigger than your opposing force. Okay? Now, you're cruising along. You slow down when you hit the 10th floor, what's going to happen to the reading on the scale? It's going to drop a little bit. Why? Does gravity become less?
No, but thanks.
What does your body want to do?
Keep going.
Your body wants to keep going at 10 meters per second or whatever that is. So the elevator is going to slow down. So for a little while, the reading on that scale is going to drop. So it's going to drop down a little bit, but then once you stop, then it's going to go back to 700. So if that applied force is bigger, you're accelerating upward. If that applied force is less, that means you're going to have a negative acceleration. Okay? That's all it means. Now, then, so as long as you're moving at a constant velocity, this is going to be a horizontal line. If you're speeding up, it's going to go up. If you're slowing down, it's going to go down like this. Okay? Got that idea? So this, now, this is your applied force. What would your opposing, the gravitational force, look like as a function of time?
Constant.
Yeah, it's just going to stay the same at negative 700, because that isn't going to change. So what you're changing is your applied force. So here's what you're going to do in the lab. You're going to take a 10 Newton scale, make sure that you re-zero it, okay? And imagine that's re-zeroed. And then you're going to take and hook this up like this. That was another failure. Okay? So when you're just holding it like this, what should be the reading on the scale?
4.9.
4.9 newtons. Then you're going to accelerate it upwards. When you're accelerating it upward, what should happen to the reading on that scale? Should go up. So is this measuring FAP, FOP, or net? Because if it was reading net force, what would it be reading right now? Zero. And it's not. If it was reading the opposing force, if I moved it up or down, what would it do? Stay the same. So because this value changes, that means that this is what's measuring your applied force. Got that? Okay. Now, that's one way you can look at vertical acceleration. Here's the other way you can look at vertical acceleration. So if I may, this, okay? So y'all have done this before, right? Hold this down, you let go of it, what happens? Does it accelerate when I let go of it?
Yeah.
So what does that mean in terms of forces?
There's an
They're
imbalance
imbalanced.
force.
There's some imbalanced force, right? Because if I let go of it and it didn't accelerate, what would that mean?
It's a balance force.
Constant
Forces are
velocity,
equal.
which is
Whatever, I don't know what the forces are, I just know that all the forces are balanced out.
And that equals 0.
Beautiful. Now, when I let go of it, clearly I get an acceleration. What's causing the acceleration?
The opposing,
Force of gravity?
Yes, FOP.
yeah, FOP is
Yes, FOP.
greater.
FOP?
FOP is greater.
FOP is greater than FAP.
The applied.
So is fat bigger than FOP or FOP bigger than fat?
Are we talking about the
FOP
stapler?
Depends which one
Talk
you're
about the
talking about.
stapler,
Are you
right?
talking about the weight or the stapler?
Okay.
The stapler?
Whoa, whoa,
Wait,
whoa,
what?
whoa, 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 whoa.
Mass.
Okay, here's the 500 gram mass over here. So what do you think is true of the mass of the stapler? Is the mass of the stapler bigger or smaller than 500 grams?
Smaller.
Smaller. A lot different?
No.
No, it isn't like I've got like an elephant on this side and the stapler over here. Okay? There's a slight difference between the two. So, but you all said that gravity is making this happen, right? Because if I let go of this and if I could shut off gravity right here, and I let go of it, what would happen? It just stayed right there. So there must be an imbalanced force. True? Now, here's what I want you to think of. I got this 500 gram mass here. What if I just cut the string? Okay? I don't let go of it. I just cut the string. So if I just cut the string, what would be the, and let's define down as being negative. If I just cut the string, what would be the net force acting on the 500 gram mass?
Negative 4.9 newtons.
Negative 4.9 newtons, right? If I took negative 4.9 newtons and divided that by the mass, which is a half a kilogram, what do you think I would get as the acceleration? Negative 9.8 meters per second squared. So if I cut the string, I get an acceleration of negative 9.8 meters per second squared. My net force is my gravitational force because that's the only thing acting on it. Now, so when I let go of it, clearly, that thing is not in a state of free fall. Okay? It's not anywhere close to that. So, but when I let go of this, is gravity still pulling down with a force of negative 4.9 newtons? Pretty much so, right? But here's the question. Then why don't I get an acceleration of negative 9.8 meters per second squared?
You have a positive
Ethan,
Holy.
not so much the pulleys.
The stapler. Stapler.
Well, what's it
is-
attached to?
string.
String,
Okay, wait, I
Okay.
get it.
right? So is the string providing an upward force? Yeah, because if the string wasn't providing an upward force and I let go of it, what would happen? So I got gravity pulling down on this string, on the mass, right? What's the direction of the force provided by the string? Upward. So on this case, which one's bigger? The tension, or the tension pulling up, or gravity pulling down?
Gravity.
Because
I mean, in that
On this one, gravity pulling down is stronger than tension pulling up. But now, over on the stapler side, what's happening?
tension is stronger than the
The
gravity.
tension pulling up is bigger than the gravity pulling down. Okay. Now, because it's the same string, do you think the tension is the same throughout the entire string?
yes.
Yeah, it is, because it's the same string, right? I can't have, like, more tension on one side than I can on the other. So the tension is the same. So what we're going to do is we're going to look at this in terms of a FAP, FOP, and FINET situation. So we're going to let the bigger mass be the applied force, okay? Because that's what's making the system go. This is going to act as the opposing force, okay? And so the difference between the two forces is going to get us our
Net.
net force. Oh, that's kind of cool. Okay, so. Did you move the camera over? We'll take that as a no. That's okay. It's all right. I'm going to draw it anyway. They heard the audio. So let's just make this simple and just say it's a one-polar system. So here's 500 grams, and there's the stapler, and let's say that that is 400 grams. So forget about the stapler. How much downward force is acting on the 500 gram mass? 4.9. Now, I'm just going to make this positive for now. 4.90 newtons. So, when in doubt, chart it out. Lay this out and go, okay, here's FAP, FOP, FINET. So in this situation, I'm going to make this be a positive number because I'm just going to make this my applied force. So I'm going to make this 4.90 newtons. So somebody take 0.4 and multiply that by 9.8. It's 3 point something.
Go negative 3.92.
3.92. Now, I'm going to make that negative because that's acting as an opposing force to the system. So I got this pulling down at 4.9, right? So this is providing basically, because of that string, a force that's opposing that at negative 3.92 newtons, because that's what's working against it. So this is being pulled at 4.9. Gravity is pulling on the opposite direction of 3.92. So how can I calculate the net force?
Combine the force.
Yes, add them together. So basically take 4.9 and add a negative 3.92. What do you get, 0.98?
You didn't label FOP.
Okay? No, it's legitimate. All right. So here's the deal. That just gives me my net force. To get my acceleration, what do I still have to do? Divide by mass. Here's the question. Which mass do I use? Do I use the 500 grams? Do I use the 400 grams? Do I
Difference.
divide by the difference of 100 grams? Or do I divide by the total mass of 900 grams? So you have four options: 900, 500, 400, 100. So how many vote that I'm going to divide by the total mass of the system? Okay? How about by the 500 grams? The 400 grams? What, you're the only one on the 400 train.
Yeah,
I
this
need to change
this
my answer.
politics part where I put my hand down.
You can change it to what?
I wanna do the total 900.
You want to do, okay, so you want to do a revote on the 900.
I'll put my vote in the 400. I have faith.
No, I'm going with the 100.
Okay, so how many votes do we want to divide by the difference of 100 grams?
I don't know. You have to add them together. The
Yes,
forces.
you have to add it together. Why?
Because you added the forces together.
Okay, look, are we just accelerating one of them?
No.
No. Do both masses have inertia?
Yes.
Or do they both want to remain at rest?
No.
Yes, they both want to remain at rest
I just answered yes and I said that.
because they both have mass, right? So this net force has to accelerate both of them. So here's the deal. Listen to me, listen to me, listen to me, listen to me. No matter what the system is, your last step is always, and I repeat, always, to divide by the total mass of the system. Always. No exceptions whatsoever. You don't divide by a single mass, you don't divide by the difference of the masses, you always divide by the total combined mass. So, great. Take 0.98 or somebody and divide that by 0.90 kilograms.
0.0.
What? 0.98 divided by 0.9.
0.9. Okay, here we go.
Here we go.
It's 1
1.09.
Okay? 1.09 meters per second squared. Okay? Good with that? Beautiful. Now, what if I put 500 gram masses on both sides?
So,
Acceleration would be 0 because your FAP would be the same as your FOP and your net force would be 0. Okay? Cool with that? All right. So, stop that and let me hit that lab. All right. So, here's what you do on the first part of the lab, on page 1. So, you're going to take a 500 gram mass on the 10 Newton scale, make sure that you bring 0 to 10 Newton scale. And basically, you're going to move it up at a constant velocity. You're going to move it down at a constant velocity. Then you're going to accelerate it upward, and then you're going to accelerate it downward. Now, if you want to get your phones and do like the slow motion thing where you can, because this is tough to see because you're accelerating it, and you can move your phone with it and record that reading, you can, or if you can just kind of eyeball it, doesn't make a difference. So, but keep in mind, what is the scale reading? FAP, FOP, or FNET?
FAP.
FAP. Just remember that. You have a 500 gram mass and the scale is reading FAP. Not FOP, not FNET. So then after that, basically all of page 1 and page 2 are a series of questions based upon that idea. When you get to questions 13, 14, 15, 16, 17, all of those deal with the limb lab, okay? But I've given you the parameters again. There's the mass of the limb, 5,000 kilograms. G on the moon is still negative 1.67 meters per second squared. Do not forget, even on the moon, you still have to pay the gravity mafia. But they just don't charge as much there, okay? But you still have to pay the gravity mafia. Now, when you get to page 3, the Atwood machine, that's technically what the stapler system is referred to as. So what you're going to do on that one, so in the spin, so you're going to take a pulley and you're going to put 200 gram masses on each side. But on one side, actually, this string is too long. I'm going to do a quick scroll adjustment here. So if I just put 200 grams on each side and let go, what's going to happen?
It's gonna stay where it is.
Yeah, nothing's going to happen, right? Why?
because the forces are balanced.
Everything's balanced out, right? So here's what you're going to do. You're going to take a 20 gram mass and you're going to put that on one side. Now do you have an imbalanced force?
Yeah.
Now what's going to happen?
Yeah.
Now it's going to begin to accelerate. So here's what you want to do is this. The 220 grams, are we going to consider that the FAP, the FOP, or the FNET?
Oh, wait, this one?
No, the 200 with the 20.
The FOP.
No.
FAP, because this is the side that's driving it. This is the side that's making it go. Okay? We're going to make this the FAP. I don't care if you make this positive or negative. I don't care. Personally, I just make it positive. So then, your opposing force is going to be 200 grams, the weight of the 200 gram mass, right? So, we're going to consider that the opposing force. And I even tell you that in the instructions below on the data table. I'm going to say, make the bigger one FAP, make the smaller one FOP, find the difference, that's your FNET. So here's what we're going to try and do. We're going to get two different accelerations. A theoretical acceleration, just like we did up there. You're going to set up a chart. Hey, here's 220 grams, 0.22 kilograms. Multiply that by your gravitational acceleration. There's your FAP. Take 0.2 times 9.8. That's going to be 1.96 newtons. That's your opposing force. So set up a chart, go FAP, FOP, FNET. Then how are you going to get the acceleration? Keeping in mind that I've got a 200, a 200, and a 20.
Your finite divided by those two. The total.
The total system. Now, that's going to get you a theoretical acceleration. We also need to get an experimental acceleration. So here's what you're going to do. So when I let go of this, what are some things that you could measure?
Time.
We could measure time. We can measure distance. Ah, okay. Now, if you're clever, and you all are, what are you going to let the initial velocity be?
0.
Oh, that's kind of cool. You can have it moving if you want, but it's going to be a god-awful amount of work. So, what relates distance, acceleration, time, and initial velocity to zero?
No.
No, that's time, Hunter.
One half,
Exactly.
well, it's V naught time, right? You're clever, so the initial velocity is going to be 0. Okay, that's kind of cool, right? So, are you going to measure how far the mass goes?
Yeah.
Are you going to measure the time involved? Yeah. Guess what? You can solve for
Acceleration.
Now, are you going to put in numbers and then solve it?
No.
What are you going to do?
Solve for A first.
So, Logan, what's this equation look like? Solve for A, keeping in mind that I load fractions.
Square root.
Oh, God, no. Oh, God, no.
Square root.
No.
No.
Get rid of the fraction first.
2D
2D. Then what?
divided by T.
Squared.
T
Perhaps T squared?
Yeah.
Because it's only the T that's squared, not the whole thing.
Okay, I got it now. Yeah.
Divide by T squared?
Yep.
Anything else? Don't make this
Equals
difficult.
A.
Keep it the same. That gives me my acceleration, right? Now, I don't care what you measure. I don't care if you measure how far one goes down. I don't care if you measure how far the other one goes up. I don't care, because it's a 1-to-1 ratio, okay? I don't care what you measure. But just make sure that you're picking the same point. Are you measuring off the top of the hook, the bottom of the hook? What are you doing? I'd recommend that you go at least 30 centimeters, okay? Just so you have, some distance to travel. Okay, don't go like a whole meter. That's going to be too far. I'd say somewhere between 30 and 40 centimeters, maybe 50 if you wanted to. So, everybody's data is going to be different. So you're going to run 5 trials with 200 and 220. Then you're going to take another 20-gram mass and add that to it. So now what do you think is going to happen to the acceleration once you put another 20 grams on there? The acceleration should get bigger. But what have you done to the mass of the system, though? I actually have more stuff to accelerate. Because now I have more mass in the system. Just something to think about. So, you're going to do, I want to see the distance. Using your average time, calculate that acceleration using this equation here. And then you do the same thing with the 240. Then down below, then you're going to do the theoretical acceleration based upon the difference between the masses. Now, you've got about half an hour. Get the data today. Okay, yes, this is due tomorrow. Get the data. This goes relatively quickly. That takes some time. Okay? Any questions? Now, If you want water, I got the water refilled, there's ice as well. If you're getting water, because I'm getting kind of screwed on this deal, because I've got like 7 cents, and a lot of that water is gone. So, I'm paying for this out of my own pocket, so help me help a brother out here. Okay, go.